Nuclear physicist Vernon R. Kupps writes, "The only places that might be hot enough to produce heavy elements are supernovas, yet their energy is several orders of magnitude less than that required to produce the heavy elements. The alternative theory is stepwise direct nuclear reactions. Several problems exist with this theory. First, the sequential nuclear reactions on the same nucleus become increasingly improbable in a large aggregation of target particles. Second, there is no way to observationally determine whether any heavy nuclei observed are primordial or manufactured later. Third, there is no source for the neutrons needed for this theory. Finally, how are any of the heavy nuclei produced by this method distributed around the universe?" Physicist John Hartnett and researcher Alex Williams highlight another problem. To get enough supernova explosions, they have to postulate many generations of early massive stars of about 100 solar masses each that die quickly within about 1 million years, exploding and producing stardust that gets recycled into new generations of stars, and so on. The problem here is that such massive supernovae do not just produce stardust, they also produce very stable remnants, black holes. In our galaxy, there are about 10 to the 11th stars, and about 3% of the galaxy mass is in the form of gas and dust clouds. If the primordial galaxy contained only massive stars of about 100 solar masses each, when they exploded they should have left behind about 10 to the 9th black holes, each containing about 10 solar masses of material. The rest is blown off by the explosion and becomes stardust. If there have been many generations of such supernovae that have also left behind equivalent numbers of black holes, then black holes should be about as numerous as stars in our present-day galaxy. This has disastrous consequences for stellar evolution. With so many black holes about, they would get caught up in subsequent cycles of star formation and gobble up the ingredients so no further stars could form. It also contradicts the observational evidence. We have only about a few dozen candidates for black holes in the Milky Way. Even assuming the theory is true, the process has to be extremely fine-tuned. Physicist Fred Hoyle, who discovered this fine-tuning, wrote, "A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question." Physicist Rodney Holder writes, "One of the most famous examples of fine-tuning is that discovered by Fred Hoyle. The ratio of two of the fundamental forces of nature, the strong nuclear force, which binds atomic nuclei together, and the electromagnetic force, which operates between charged particles, has to be just right for carbon and oxygen to be made inside stars. The value it takes ensures that there is a resonance in the carbon atom at the right level to make carbon production efficient, but no resonance at a level in the oxygen atom that would make all the carbon turn into oxygen." It is worth repeating Hoyle's comment here, when he made this discovery, that a super-intellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. It is very significant that this is a man who earlier in his life described religion as an illusion. Physicists Luke Barnes and Geraint F. Lewis write, "A good example of the way this field has progressed is the work of Ulf G. Meissner and collaborators. His team of experts in the theory of nuclear forces turned their attention to the Hoyle state of the carbon nucleus. As we saw in Chapter 4, this state plays a crucial role in the production of carbon in stars, and hence the manufacture of the backbone of DNA and a host of other biological building blocks. In 2011, they used supercomputer simulations to show that nuclear theory can correctly predict all the measured properties of the Hoyle state. In 2013, they used their state-of-the-art model to investigate the, quote, viability of carbon-based life as a function of the light quark mass, unquote. They calculated that changes in the masses of the quarks or the strength of electromagnetism of more than a small percentage significantly affect the ability of the universe to produce both the carbon and oxygen required by organic life." Holder writes, Atheist physicist Victor Stenger questions the fine-tuning of the Hoyle resonance described earlier. Yet, as Barnes notes, the most recent studies show this fine-tuning to be robust, especially taking into account the requirement that stars produce both carbon and oxygen, not carbon or oxygen. Thus, Oberhammer et al. Show that, with a change of 0.4% in the strength of the strong force, carbon-based life appears to be impossible, since all the stars then would produce either almost solely carbon or oxygen, but cannot produce both elements. Here are some of the studies that he cites. Barnes and Lewis write, Steven Weinberg argued on plausible grounds that the Hoyle state would have life-permitting properties for a large range of parameters. This has since been shown to be incorrect by the calculations of Eppelbaum et al. And Meissner. And here are the studies that they cite. Hoyle wrote, "It is because of this incredible chain of subtlety that I doubt the 19th century denial of a purposive universe. If this were a purely scientific question, and not one that touched on the religious problem, I do not believe that any scientist who has examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside the stars." Astronomer Owen Gingrich writes, "I am told that Fred Hoyle, who together with William Fowler first noticed the remarkable arrangement of carbon and oxygen nuclear resonances, has said that nothing has shaken his atheism as much as this discovery. From time to time I sat with Fred Hoyle, generally discussing one historical issue or another, but I never had quite enough nerve to ask if this discovery had shaken his atheism.
Carbon is the key atomic building block of all organic matter, the basis for the molecular machines inside our cells, for the petals of flowers and the bark of trees, for the antlers of elk, and for the skin of a newborn baby. Carbon has an enormous and unique capacity to form multiple yet stable chemical bonds, both with itself and with other elements. In theory, carbon can form a virtually infinite number of different chemical compounds. More than 65 million carbon compounds have actually been identified, with more being discovered all the time.
If you look at the properties of the carbon atom, it's the only atom in the periodic table, really, that you can build lots of a vast diversity of complex chemical compounds with. And I would assume that, like everybody else, like NASA and everybody now, that if you're going to build complex, self-replicating chemical systems, you're going to have to choose the carbon atom.
There is no other known element in the universe that can substitute for carbon. If carbon were to disappear tomorrow, complex life like ourselves wouldn't just dwindle, it would cease to exist. Carbon is especially fit to make life possible in the environment found here on Earth. That's because carbon compounds needed for complex life are only stable within a narrow range of temperatures. The range of temperatures that just happens to be found on our planet. If temperatures on Earth were higher, like on the surface of Venus, carbon compounds would no longer be stable, undermining both the creation and perpetuation of complex life. If temperatures on Earth were lower, like on Uranus, the chemical reactions creating carbon compounds would be so slow that life could not arise here for tens of billions of more years, if ever. Not only do carbon compounds make life itself possible, they make our current human technological civilization possible. From the vast cornucopia of carbon molecules that fill our planet, we obtain natural gas, petroleum, clothing, sugar, plastics, and anesthetics. Some have proposed that alien life forms might exist based on silicon rather than carbon. But most experts think that idea is the stuff of science fiction rather than science. In fact, the uniqueness of carbon has led one astrobiology textbook to suggest that if aliens were ever to visit the Earth, we should welcome them with carbon-based cakes rather than silicon-based rocks.
I came here to give you these facts.